Is my screen visible?
Yes, sir.
Okay. So we were talking about the transformation matrix, how you can transform from one basis to another basis. Okay, and that is by this is the way we do it. We need a transformation matrix. We need a matrix which gives us this transformation from the first basis to also the second basis. And example was that of transformation from Cartesian coordinates to from spherical coordinates to Cartesian coordinates. So this was the transformation matrix. So if you want the transformation to be both ways, then it must be a invertible matrix. That means its determinant must be equal, must be non-zero. Okay. Next, we go to the concept of a scalar product. So scalar product, the idea is very similar to your dot product. Okay, scalar product, the idea is very similar. Okay, similar to the concept of, in fact, the dot product is, specifically speaking, the dot product is nothing but the scalar product. Okay, that is dot product, because this is something that you are familiar with in vectors. Dot product in vectors. Okay, so that's the scalar product. So suppose I'm having two members of a vector space f and g, then the scalar product is written in this way. Okay, inside angle brackets f g with a bar on in between the two. Okay, so suppose I'm having two members f and g which belong to a vector space. Their scalar product is given in this way. So this is equivalent to the ordinary dot product in ordinary vector space. Ordinary vector space, A is one vector, A is one vector, and B is another vector, and we find out the dot product of A and B. Okay, so that is basically what your scalar product is. Okay, so there are two features for a scalar product that you need to always keep in mind. There are two features for the scalar product. First is the scalar product of a member with itself. You can find out because it can be any two members. So f and g can be any two members. So I can choose f and g to be the same member itself. Nobody is stopping me. So that is known as a self-scalar product or a scalar product with itself. So the scalar product of a vector with itself must evaluate to a numerical value. Okay, it must give you some numerical value. So scalar product of a vector by itself is equal to some numerical value, some result that is going to be equal to lambda. Over here, this lambda could be a real number or it could be a complex number. Okay, so scalar product of a member with itself will always evaluate to a numerical value. Second main feature is the scalar product must be linear into each of the two members. Okay, so let's say I'm having three members, f, g, and h, and I take a sum of g and h, and I find the scalar product of f with the sum of g and h. So this scalar product is the same as, you could just open this up, it is same as scalar product of f and g plus scalar product of f and h. Okay, likewise, instead of taking f scalar product with g plus h, if I take f plus g and then take the scalar product with h, this is the same as scalar product of f with h plus the scalar product of g with h. So this is how the scalar product is defined. Okay, this is how the scalar product of two members of vector space, this is how it are defined. It should contain these two features. Then for members of a vector space which are functions, for vectors, ordinary vectors, it is very easy. You can test for yourself. This indeed is true, because we can see here, suppose I'm having two vectors, vector A, okay, and vector B. So scalar product, how do you take? Okay, for vectors, for scalar product, we just put a dot, right? So if I have vector B plus vector C, okay, so this is equal to, so this is nothing but your vector A scalar product with vector B plus C. Okay, let me write it bigger. So let's say I'm having vectors, vector A, I want to scalar product with vector B plus vector C. Okay, in case of vectors, what we have, first vectors and second vector, just put a dot in between. So first vector is A and the second vector is B plus C. Second vector is B plus C. And this is equal to, you know, from vector operation is distributive. So this is going to give us A dot B plus A dot C. So which you know is nothing but A scalar product B, scalar product of A and B, plus the scalar product of A and C, which is basically this. Similarly, you can verify for this also. For vectors, this will also work. Okay, is that clear? All right, so instead of vectors, let's say we have functions. Okay, if the members of the vector space, they are functions. In that case, how do we define the scalar product? In that case, we define the scalar product in this way. Okay, we define the scalar product in this way. That is, scalar product of one function with another function is defined as an integral. You are basically integrating the conjugate of the first function. So whatever you put, okay, so when I say scalar product, so when I write something like this, so this will be the first function. This is the first function, and this is the second function. This is the second function. Okay, so when I say scalar product, if we are talking about functions, the first function, that is whatever function is on the left side of the bar, and whatever is on the right side. So this is the left side and this is the right side of this bar is the reference. Okay, this bar is the reference. The function to the left, function to the right. So the function which is on the left side of the bar, that is the first function. The function on the right side of the bar, that is the right function. So if I have a scalar product like this, if I want to take something like this, so then what I have to do is the function which is on the left side of the bar, you have to take the conjugate of this function. Okay, then you take the function which is on the right side of the bar, okay, as it is, don't take the conjugate. So conjugation always has to be done only for the first function or the left function. Take the product of these two, multiply this with some other function w, and integrate between a and b. Okay, so here this a, this b, and this function, okay, this w function, it depends on the particular definition of the scalar product that we wish to adopt. What kind of scalar product you want to adopt? So it depends on basically that. Okay, so it could change from vector space to vector space. Okay, so that's what basically your scalar product is all about. The integration, okay, by the way, last point that I have forgotten. The integration equation number 1 is indispensable. We have to integrate. Okay, there's no escape from this. You have to integrate. This is very much required. This integration is required, and this allows us to generalize the concept of the scalar product. So the integration is required for the generalization of the scalar product. Okay, so for example, electron spin space, which is spanned by alpha beta. Okay, so alpha is one spin state and beta is another spin space. Okay, so let's take this as example. So we define the scalar product in a certain way. So it's up to us how we define the scalar product. So we define the scalar product in this way. We define the scalar product in this way such that if you take the scalar product of alpha with itself or beta with itself, the result is 1. Okay, that's one definition. Another one is if you take the scalar product of alpha and beta or with beta and alpha, that is alpha is the left function and beta is the right function, or you take beta as the left function and alpha is the right function, then the result is 0. So how do you define the scalar product? We define as if both the vectors are the same, then the scalar product will take the value 1. If the two vectors, they are not the same, if the two vectors are different, then it will take the value 0. So that's how we define the scalar product between A and B in an electron spin space. So suppose I have two 1 electron functions. Now you remember this is the basis. Okay, remember this is the basis. Okay, this is the basis. So I could have, the spin. Okay, in general, I could define the spin in this way. I could define the spin as first function is alpha. To that, I multiply some constant a1. And the second function is beta in this basis. The second function is beta. To this, I multiply some other constant, which is a2. Okay, so I could always do that. So this is, in general, this is how you write down functions. Likewise, I could have some other function, g. The basis is the same, right? Basis is alpha and beta. It just matters, what matters is what you're multiplying. Here I'm multiplying b1 and b2. So these are two. In general, this is one spin state. It is a superposition of alpha and beta. This is another spin state, which is a superposition again of alpha and beta. Okay, so that's how we have written this over here. Okay. So what is the scalar product? Okay, let me just work this out. Okay, let me write down the scalar product here, so that because the steps are not worked out here. So I want to find out the scalar product of f and g. I want to find out the scalar product of f and g. So the way to go about finding the scalar product is I need to first expand this. Okay, I need to expand this f as well as g. What is f? F is A1 alpha plus A2 beta, and J is B1 alpha plus B2 beta. This is what we have. Okay, so now how do we go about working this out? We use those features, remember those two features, this feature, right? We can use this feature. Okay, so we can expand. So if you combine these two, if you just combine these two, what does this give us? So if I have a plus b, vector a plus b and vector c plus d, what is this going to be equal to? This will be, first take a, so we have scalar product with a and c, then scalar product with a and d, then you take b, scalar product with b of b and c, and lastly scalar product with of b and d. Okay, so this is what we will have, right? So we use the same idea over here also. Okay, so this will be scalar product of A1 alpha with B1 alpha, B1 alpha. Next, the scalar product of this with this one. Scalar product of A1 alpha with B2 beta. Next, we have scalar product of this one, A2 beta with B1 alpha, that is this one, B1 alpha. And lastly, we have A2 beta and B2 beta, A2 beta and B2 beta. Now this A1, A2, B1, B2, all of them will come outside. So here we will get A1, B1. Over here we'll have A1 and B1. These are constants, so they will come out. What is left behind is scalar product of A1, sorry. What is left behind is scalar product of alpha and beta, alpha and alpha, alpha and alpha. Next we have A1, B2, A1, B2. Then we have scalar product of alpha and beta. Next we have A1, A2, B1, A2, B1, scalar product of beta and alpha. And lastly we have A2, B2, A2, B2, scalar product beta and beta. Okay, so now we know from this definition. Okay, so from this definition we already know. Okay, we have defined it this way: scalar product of alpha with alpha is 1, scalar product of alpha and beta or beta and alpha, this is 0. So that means this is going to be equal to 1, this is going to be equal to 1, and this is going to be equal to 1, this will be equal to 0, and this also will be equal to 0. So as a result, this scalar product of f and g will be simply equal to a1 b1 plus a2 b2. So this is what you will get. That's the scalar product of these two spin states. Is that clear, everyone?
Yes, sir.
Okay, the same thing I've given over here. I just showed you the steps. All right, so now once we have defined the scalar product, so we have learned two concepts. Okay, we have learned two concepts since yesterday. We have learned about vector space and we have learned about scalar product. So we have learned about vector space. This is one concept that we have learned about, and today we have learned about another concept which is known as the scalar product. Okay, both of these together will give us a very, very special vector space, and that is known as a Hilbert space. Okay, so this is what we are interested in. Any vector space for which the scalar product is defined. Any vector space for which a scalar product is defined, that is known as a Hilbert space, to put it simply. So a vector space that is closed under addition and multiplication by a scalar, and which has a scalar product that exists for all pairs of its members, is known as a Hilbert space. So if you're asked what is a Hilbert space, this is what it is. This is the definition. Okay, Hilbert space is a special kind of a vector space. In this vector space, it is closed under addition and multiplication by a scalar, which is true for all vector spaces, all linear vector spaces. In addition, in that vector space, if the scalar product also exists for any pair of members, so if I take any two pairs of these members, there exists a scalar product, then such a vector space is known as a Hilbert space. So Hilbert space, remember, it's a special case of a vector space. It's a special type of a vector space. Okay, so what are the properties of Hilbert space? Important, you need to know what the properties of Hilbert space are. So first property is closure. So suppose I'm having members f, g, and h, which are subject to two operations. The two operations are addition and multiplication. Both of these operations produce quantities which are also members of same Hilbert space. So if I have, let's say, some Hilbert space. Okay, so let's say this is a Hilbert space. Okay, this is Hilbert space. So this is one member, this is another member, this is another member, this is another member. So let's say this is member A, this is member B, this is C, and this is D, and so on. So if I take any two members, let's say, okay, so this is B. So if I say I take member C and member B, and if I do operations, let's say I do B plus C, if I do, okay, then this B plus C will also be a member. So if I take this operation, if I do the addition operation, okay, and I get, let's say, B plus C is also going to be a member of the same Hilbert space. So this is meant by closure. It's closed. Okay, you do these two operations, the result that you'll get, that will also be a member of the same Hilbert space. So that's closure property. Next, addition is commutative and associative. Okay, addition is commutative associative. So to take two members of a Hilbert space, whether you do f plus g or g plus f, this is same. That is commutative property. Associative property, if I take three members f, g, and h, so whether you first add f and g and then h, or first you add g and h and then you add f, it's going to be exactly the same in both cases. So addition is associative and commutative both. Next is multiplication by a scalar is commutative and associative. So if I have some constant k, okay, so if I have some constant k, then I can multiply this constant to this vector. So whether you pre-multiply this or you post-multiply this, the result is going to be the same. Next, if I have two members of the Hilbert space and I take the sum of these two, and then after taking the sum, then I multiply the constant, that is the same as first multiplying the constant and then taking the sum. Next, let's say I'm having two constants and one vector from the Hilbert space. Then if I add the two constants and then multiply, that is the same as first multiplying the two constants and then adding them together. And lastly, if I have again two constants and I have a member of the Hilbert space, so whether I first multiply a constant and then multiply the other constant, so whether I first multiply one constant to the vector and then multiply the other constant, or whether first I multiply the constants and then multiply those with the vector space, the result is going to be also the same. Okay, so this is your commutative property, associative property, and the distributive property. So this is commutative, this is commutative, okay, and this is associative, this is commutative property, this is associative property, and these two are distributive properties. These are the distributive properties. Next, we have completeness. Any Hilbert space is spanned by a set of basis functions. Okay, so it means Given a Hilbert space, it will always have a set of basis functions. So that's the property of completeness. So why it's called completeness means each and every member of the Hilbert space, each and every member of the Hilbert space can be represented by the linear form like this in terms of the basis member functions. So this is meant by completeness. That means there is no member which cannot be written like this. So it means every member is complete and can be written in terms of the basis functions. So that's the completeness property. Okay, so then what do we have next? Yeah. So we have, suppose any two members of the Hilbert space, okay, F and G. And one of the things about Hilbert spaces, the scalar product is defined. That means there exists a scalar product between F and G. Okay. And this scalar product, it evaluates to a finite real or complex numerical value. It means it should have some numerical value. When I say numerical value means it will be independent of S. S is the variable. Okay. So when I say it should have a real or finite, real or complex numerical value, this means it will be independent. The scalar product will be independent of this variable S. And this has got the following properties. First is the scalar product of F with itself will be always positive. Okay, will be always greater than equal to 0, and it will be equal to 0 if F is the 0 vector. If it's F is a 0 vector or a null vector, in that is the only case in which this equality is going to become an equal to, sorry, this inequality is going to become an equality. Then from here we define something called as a norm. Okay, how do you define norm? Norm is simply root over the scalar product of a vector with itself. Okay, in a Hilbert space, the norm of a vector F is defined simply as the square root of the scalar product of the vector with itself, and it is given represented this way. So this is equivalent to the magnitude. This is equivalent to the magnitude of a vector. Okay, so if you remember, so I have, let's say, a vector A. Okay, I have, let's say, a vector A. Let's say this is equal to ax into x cap plus ay into y cap plus az into z cap. Then what is the scalar product of A with itself? This is equal to simply A dot A, right? This is simply A dot A, which is equal to, which you already know, ax square plus ay square plus a z square. So what will be under root? What is under root? What is under root ax square plus ay square plus a z square? What is under root? This is basically under root this one, and this is your norm, right? This is your norm. So which is the same as the magnitude of a vector. So norm becomes the magnitude of a vector in case of ordinary vectors. All right. Conjugate of a scalar product, very simple. So we have scalar product, remember, F and G, right? So we had, this is the left and this is the right function. And if you remember, how did we define this? Lower limit to upper limit in general. This is whatever is the left function, you have to take the conjugate. Whatever is the right function, you have to take it as it is. Then there will be some other weight function called as W, which is a function of S, of course, into ds. Now, if I take the whole thing, if I take, the whole thing, if I take conjugate of this one, this entire thing, if I take conjugate, then what will happen? If I take the conjugate of the entire thing, this will be equal to A to B. Then we are taking conjugate, F conjugate, that is going to give us F, and then G conjugate, W, it's a real function, so it remains unchanged. This is what it is. So now here we are taking the conjugate of what? We are taking the conjugate of G. That means, this means G becomes the left function, because you can see here, whatever is a left function, that's what we are taking conjugate of. Now G is being conjugated here. So G must be the left function and F must be the right function. So that's what you have. If you put the conjugate outside, you have to change the order inside the scalar product. If it is GF star, that is same as FG. Okay, is this clear? Then next one is fg plus h is equal to fg plus fh. Okay, this you're already familiar. This also you are familiar. And this one, if k is a constant, you're familiar with this. Okay, now here, how did we get this? Also, same way as this over here. So I want to find out k, f, g. This is what I want to find out. So this kf is the function. So according to this definition, so we have a and b. This is the left function, this is the right function. So whatever is the left function is kf. You have to take the modulus of this one. Okay, sorry, you have to take the conjugate of this. Then g w of s into ds. So this one is nothing but a to b. This is nothing but k conjugate f conjugate g w ds. So now this k conjugate is going to come out. Integration from a to b f conjugate g w ds. So we have k conjugate, and this is nothing but your scalar product f g, and that's how you get this result. Okay. Likewise, we have this one also. This is very straightforward. You can just verify each and every one of them. Okay, please verify this. Okay, each of these. I have already done some of this. Please verify this. Okay. And finally, we have this. Okay, this one also. Verify this as well. Okay, then we have something called as the Schwarz inequality. Okay, what is the Schwarz inequality? It says that the scalar product that meets the Hilbert space conditions will satisfy the Schwarz inequality. Okay, the scalar product that meets the Hilbert space conditions will satisfy the Schwarz inequality. Just give me a second, okay? Okay, so what the Schwarz inequality, it says that if you take the scalar product of any two vectors, okay, and you take the whatever is the result, you take the magnitude. So this will be always, this is guaranteed that this quantity will be real, okay, because in case the scalar product gives us a complex number, then you're anyway taking the modulus square, so that is going to give us real. So this will be always less than or equal to the product of the individual scalar product, individual square of the norms, that is self scalar product. Okay, the product of the self scalar products of f and g. So that is your Schwarz inequality. Okay, in terms of ordinary vectors, this is one, I think you are familiar with this. Okay, this relation, that is if I say vector a and vector b, a dot b is ab cos theta, right? A dot b in ordinary vectors, it is nothing but ab cos theta. So therefore, if I say modulus a b squared, what will this give us? It will give us a square b square into cos theta, cos square theta. Okay, now cos square theta will always be less than equal to 1, yes or no? Because the cos function, right? This is how a cos function looks like. This is how a cos theta function look like. Then what will be a cos square function? So cos square function will be something like this, right? So it will be between 0 and 1. So cos square theta will always be less than equal to 1. So if cos square theta is less than equal to 1, that means a square b square, multiply both sides with a square b square. A square b square cos square theta. This will also be less than equal to a square b square. And what is a square b square? A square b square cos square theta. This is nothing but a dot b whole square, and this will be less than equal to a square and b square. And this we already know, right? What is this? A dot b is nothing but the scalar product of a and b, right? A dot b is nothing but the scalar product of a and b. This will be less than, what is a square? This is nothing but the scalar product of a with itself. And what is b square? This is the scalar product of b with itself, right? So which is essentially the Schwarz inequality. So in ordinary vectors, this is what is equivalent to. Any questions so far? Any questions? This brings us to next to the idea of orthogonality. Okay, the idea of orthogonality. So you already have some idea about orthogonality. Orthogonality implies perpendicularity. We can talk about two vectors being orthogonal. So suppose I'm having one vector, right? We can talk about one vector, that is a vector A, and another vector, vector B. These two vectors are perpendicular. So A is perpendicular to B, implies we say that A and B are orthogonal. A and B are orthogonal. Fine. So now compare it with this one. So how will you say two functions, when are two functions, let's say f and g, are orthogonal? Can we think about like something like a perpendicularity? Two functions, when are they perpendicular? We don't use the word perpendicular, we use the word orthogonal. So when can we say that f and g are orthogonal? So when are f and g orthogonal? You could think about this. When do you say that two vectors are perpendicular? When are two vectors perpendicular? How do you check whether two vectors are perpendicular or not? What happens to their dot product? If two vectors are perpendicular, what happens to their dot product?
0.
It will be 0. So in the same way, if you want to find out whether two functions are orthogonal or not, all you need to do is find out their scalar product, because dot product is the same as the scalar product. So if their scalar product is 0, then that means they are orthogonal. And it does not matter whether you take fg or gf. Doesn't matter. Both cases will be 0. Okay. So let's take this example of just 1 second. Yeah. Okay, I think something is missing here on the slide. Let's see. Okay, I think I had forgotten to put one line here. Two functions are said to be orthogonal. The definition I had forgotten to put here. Okay, I'll do that. I'll make the correction here. So let's just evaluate this and see if this really works. Okay. So I have, let me clear this first. So I'm having a vector space whose bases are P0, P1, and P2. Okay, and I have a scalar. I assume a scalar product which is defined in this way. Here A is -1, B is 1, and W, because you remember the scalar product in general, F, G in general. How do you define the scalar product? We had a lower limit and we had an upper limit. Then we had first function, and the second function. Then we had a function of W. Right, this is how we had defined a scalar product. So if you compare this, A is -1, okay, and B is +1, and W, there is no W here, that means W of S must be equal to 1. Okay, so with this, we'd like to evaluate these P0, P1, the scalar product of P0 and P1, that is this and this, the scalar product of P0, P2, P1, P2, P0, P0, P1, P1, and P2, P2. Let's try this out. For that, let me just grab this portion. Okay, so this is what we have. This is how so we have a vector space which is defined by this basis and a scalar product which is defined in this way. So is this a Hilbert space? This is a Hilbert space, okay? This is a Hilbert space. Okay, because for Hilbert space, what do we need? For Hilbert space, we need, did I write it here somewhere? No. For Hilbert space, what do we need? We need a vector space. We need a vector space, and which is spanned by a basis, and we need a scalar product. So here a vector space is given, which is spanned by this basis, and a scalar product is given. So this is a Hilbert space. So the vector space which contains all the quadratic polynomials of S. Okay, so that's a Hilbert space, and we are having a scalar product which is defined in this way. So let's do one or two of these. So let's see. All right, let's try this P0, P1. Okay, the first one. Okay, I want to do the scalar product of P0, P1. So this will be equal to, the way it's defined is like this. So we'll use the very same definition. Lower limit is -1, upper limit is +1, which is F. Well, F is P0, right? F is P0. So you have to put F star. What is F here? What is P0 here? P0 here is 1, which is real. So 1's conjugate is 1 itself. 1's conjugate is 1 itself. What about P1? P1 is S. And what is W of S? W of S is 1. Okay, into ds. So this you can easily evaluate. So this will be equal to integration of S, which is S square divided by 2. S square divided by 2. We need to put the upper and the lower limit. The lower limit is -1, upper limit is +1. Because it's a square, it does not matter. Upper limit 1 square is 1, -1 square is also 1, so the result is 0. Okay, so the scalar product of P0, P1 is 0. What about P0, P2? Let's try P0, P2. P0, P2. P0, P2. What will this be? -1 to +1. What is P0? P0 is again 1. What is P2? P2 is 3 by 2 S square minus half. Okay, P2 is 3 by 2 S square minus half. W is 1 into ds. Okay, so what will this be? This will be integration -1 to +1, 3 by 2 S square into ds minus -1 to +1, 1 by 2 into ds. What will be this one? The first one will be, of course, 3 by 2 as it is. Integration of S square is S cube by 3. And you have to put the lower limit -1, upper limit +1, minus half. Integration of ds is S. So -1 till +1. Please evaluate this and tell me what you get. 3 and 3 gets cancelled. This 3 and this 3 gets cancelled. So we have 1 by 2, S cube and S. S cube, that means 1 cube is 1. Then -1 cube is -1. So 1 minus -1 will give us a 2 here. Same thing. 1 and -1 is 2. So 2 by 2 minus 2 by 2 is going to be equal to 0. So we get a 0 here. Okay. Next we have P1, P2. P1, P2. Same way as before, the limits are -1 to +1. Then what is P1? P1 is equal to S. P1 is equal to S, and P2 is equal to 3 by 2 S square minus 1 by 2. W is equal to 1 into ds. Then what do we get? So we have 3 by 2, take it outside, 3 by 2, 3 by 2, take it outside. So integration from -1 to +1. S into S square will give us a S cube into ds. Then we have minus 1 by 2, integration from -1 to +1, S into ds. Okay? And if you work this out, this also will become equal to 0. Is that clear?
Yes, sir.
Is that clear? So please try out these, okay? These three, remaining three, this, and this. Please try this out. Do this as your homework, okay? All right, yeah, it's given here. What I wanted to show over here, it's given over here. Okay, so two functions are said to be orthogonal if their scalar product is 0. Either fg or gf, either of them, if they're 0, then the two functions are said to be orthogonal. So example, p0, p1, p2, in this case, okay, p0, p1, and p2. P0 and P1 if I take scalar product, or P0, P2 if I take scalar product, it is going to be 0. So they are all orthogonal. So this set, P0, P1, P2, they're all orthogonal. You can see here, P0 with P1, we got 0. P0 with P2 is 0. P1 with P2 also is 0. Okay. So when you take the scalar product of each of these, you're getting 0. So that means they're all orthogonal. Then further, there is another quality called normalized. Okay. You'll find that when you do this problem, you'll find that these three are definitely not 0. These three are definitely not 0, but they are not 1 also. Okay, so a function f is said to be normalized if the scalar product of the function itself, okay, the scalar product of function itself is equal to 1. If you take the scalar product of the function with itself, then, and if the value is 1, then it is said to be normalized. So then these two ideas, orthogonality and normalization, we combine these two ideas and we call them as an orthonormal set. In your quantum mechanics, you would have probably come across this idea of this orthonormalization, right? So we have eigenfunctions, right? You all are familiar with this, right? So we have eigenfunctions in the time-independent Schrodinger equation. If you want to solve the solutions, they are eigenfunctions, and these eigenfunctions, they're going to form an orthonormal set, because the eigenfunctions, they must be normalized. Why should they be normalized? Because this modulus square of the eigenfunctions, that is going to give us the probability of finding a particle, okay, at a particular location. So if I take the integration over all values of x, then that is going to give us, that has to be equal to 1 for eigenfunction. I'm talking about quantum mechanics, okay? So it should be equal to 1. So that means normalization condition is satisfied, okay? I can just try this out. So time independent, oops. For instance, if I take the time independent Schrodinger equation, the time independent Schrodinger equation, okay? Time independent Schrodinger equation. So we have many eigenfunctions, let's say, right? So we have, let's say this is an psi n, let's say these are different eigenfunctions. So if I take, let's say, the integration from -infinity till +infinity, let's say psi1 star, psi1 into dx, what will this be? This will be equal to 1. But if you look at it, if you look at this is exactly the same as your scalar product, because suppose I'm having one wave function psi1, okay, let me give some other value, let me give some other index, psi m, let's say psi m of x, okay, and then I take the conjugate of this one and some other wave function psi n of x, okay, and then multiply with this and integrate from -infinity till +infinity. So over here, there the lower limit is -infinity, the upper limit b is +infinity, and the weight function, that is equal to 1. So this is nothing but, do you agree? Yes or no? Do you agree or not?
Yes, sir.
I'm talking about this one, quantum mechanics, okay? Time independent Schrodinger equation. So this must be, this is nothing but your scalar product. So this quantity that I'm trying to find here, it's a scalar product. So in the time independent Schrodinger equation, let's say you take the example of, let's say, harmonic oscillator, or let's say particle in a box. So over there, you'll get a set of eigenfunctions, right? You'll get a set of eigenfunctions psi n's, right? So if I take this, I'll get one. But on the other hand, if I integrate, let's say, psi 1 star and psi 2 dx, this will always be 0. So you will get something like this. We can write this as delta mn. Okay, so that means because of this, the set of all the eigenfunctions, the set of all these eigenfunctions that we have, this set of eigenfunctions, okay, they form an orthonormal set. That means this set of this eigenfunctions can be used as a basis. It can be used as a basis, because if it's an orthonormal set, that means they must be linearly independent. All these psi i's, they must be linearly independent. And remember the three theorems that we did, that linear independence, it implies that this can be used as a basis. So if it can be used as a basis, in general, if I have a solution, in general, if I have from the time independent Schrodinger equation. By the way, does anybody remember the time independent Schrodinger equation? Does anybody remember the time independent Schrodinger equation? Mafidul, are you there? Mafidul? Who all are here?
Yes, sir.
Yeah, do you remember the time independent Schrodinger equation? Hamiltonian psi is equal to E psi, right? This is the Hamiltonian operator, right? When the Hamiltonian operator operates on psi, we'll get some energy, some constant energy into psi. So this is a stationary state, right? So now, what is the solution? What is the general solution? What is the general solution? What is the general solution of this psi? Oops, psi of x, because it's time independent. What is this general solution? How can you write down this general solution? If you remember, how do you write down the general solution? N equals 0 to infinity, some constant Cn into psi n, right? What are these psi n's? These are your eigenfunctions. So the general solution is a linear combination of the eigenfunctions. So the eigenfunction is basically a basis. Okay, so the eigenfunction, the set of eigenfunctions that forms a basis for the given problem. Let's say you have a harmonic oscillator. So all these eigenfunctions, they are going to be solutions of the time independent Schrodinger equation. They're spanned by a basis. And what is the basis? The basis is the set of eigenfunctions. Does that make sense? Are you all able to relate what we are doing over here?
Yes, sir.
Good. So you just take this, whatever ideas that we have got so far, and just apply this to, let's say you pick up any problem, any time independent Schrodinger equation problem. It could be a particle in a box, it could be the harmonic oscillator, right? You could, or it could be even the hydrogen atom, because hydrogen atom, you have to separate this into the time dependent and the time independent parts. You could just apply this over here, and then you'll find that actually it makes sense. So this is the reason why you need to study vector spaces. Okay. Let me clear this. Okay, so a set of functions which is both normalized as well as mutually orthogonal. Okay, so any member from an orthogonal set which is not normalized can be made so by rescaling it as this one. So if a function is not orthogonal, we can normalize this. Does this sound familiar? If a function is not normalized, it's a member of an orthogonal set, but it is not normalized, we can normalize it by using this. Does this seem familiar? This one, this idea, does it seem familiar? Remember this? Normalization of wave functions, remember? Yes or no? Normalization of wave functions, remember or not? So let's say I have a wave function. Let's say I have a wave function psi. Okay, it's a let's say time independent parts. So psi of x, or let's say I take capital psi. It's a function of x as well as t. It's a function of x as well as t. Let's say for a free particle, a e to the power I kx minus omega t. Let's say a free particle. Let's say we have this one. What is the normalization condition? What is the normalization condition? Because this is not normalized. So what do we do? What do we do? We need to find out this a, right? So how do you find out a? We basically normalize this. That means we take the self-scalar product. So how do you normalize this? What is the normalization condition? The normalization condition is psi star psi into dx. This is equal to 1. This is a normalization condition. And from here we have a, right? So we have a e to the power minus I kx minus omega t e to the power I kx minus omega t into dx. This is equal to 0. This you can solve. This you solve. And from here we find out what is a. Right? We find out what is this a. And that a you substitute. Whatever a you get, you substitute it back over here. Then we say that this has got normalized. Do you remember doing something like this?
Yes, sir.
So this is what is meant by normalization. Okay, it's the same thing. So there is a one-to-one relationship between whatever you have done in quantum mechanics and what we are doing right now. All right. So if phi n represents an orthonormal set of bases, then it must satisfy this condition. So any basis which satisfies this condition is known as an orthonormal set of bases, where this delta ij is a Kronecker delta function. You remember what is the Kronecker delta function, right? So delta ij, what is the Kronecker delta function? It can take two values. Either it can take 0 or it can take 1. It will take the 0 if I is not equal to j. It will take the value 1 if I is equal to j. So that's your Kronecker delta function. So let me stop here. This will be a good time to stop, because next we will be doing how we can expand a function or using an orthogonal set of basis vectors. Okay, the general prescription of doing this orthogonal expansion. So that's what we'll be exploring next. All right. You have an exam tomorrow, right? So I think this will be a good time to stop. Any questions do you have?